He will not force
Okay, let's move away from somebody whom nobody wanted to admit being influenced by to someone who had a very great and overt influence in 17th century science, Robert Boyle. Probably one of the two greatest scientists of the century, along with Isaac Newton, certainly in Britain. Boyle was interested in chemistry. He worked in Oxford. And in trying to make sense of chemical behavior, he speculated that material substances are composed of lots of corpuscles, like atoms. He didn't use the word atom. Why not? Well, the word atom was associated with atheism, with Epicureanism and Lucretianism going back to the ancient world. So he preferred the word corpuscularianism. His theory was that substances are composed of little lumps of stuff. The shapes of the lumps might change. The way they're organized, the texture, might vary in different substances. But essentially, the different chemical properties of different substances are to be explained in terms of their microstructure. Now, very importantly, Boyle's theory is different from Descartes. Remember, Descartes thought that the essence of matter is extension. Wherever you have extension, wherever you have geometrical size, you have matter. Boyle didn't say that. Boyle drew a distinction between penetrable and impenetrable extension. So matter has the property of impenetrability. One bit of matter cannot go into another. It will inevitably push it if the two are brought into contact. But in addition, Boyle made room for empty space. So Boyle was happy to accept that the world was not a plenum, that in addition to these material corpuscles that make up the substances we see, there are spaces between them, a void. That makes his theory quite a lot more powerful than Descartes'. I mean, Descartes' theory is actually rather dubiously coherent, if you think about it. Because if wherever you have extension, you have matter, then it's hard to see the difference, how you can have a difference between different types of stuff. If they are all extended and the essence of matter is just extension, then it looks like wherever you have a cubic meter of stuff, you've got a cubic meter of stuff. That's all there is to it. Whereas if you're allowed empty space as well, then you can see how you can have very easily different arrangements of corpuscles within substances, a kind of atomic theory. But his theory otherwise is in a similar spirit to Descartes. He draws a distinction between primary and secondary qualities. That name, incidentally, primary, secondary, is most famously associated with John Locke. John Locke was very much influenced by Boyle. So you draw a distinction between the fundamental properties of matter, the extension, the size, the shape, the motion, and the secondary qualities that we observe, the color, the smell, the taste, and so forth. And the explanation of the latter is in terms of the former. The reason why something has the color that it does is to be explained in terms of the microstructure, the way the corpuscles are arranged, maybe the shape of the corpuscles, the way light bounces off them, and so forth. Okay, let's go back briefly to the heavens. Johannes Kepler was an assistant of a nobleman called Tycho Brahe. Tycho built an observatory which enabled him to observe and note down the motion of the planets over many years to an accuracy far greater than anyone had previously been able to do. In analyzing these results, Kepler, after Brahe had died and he'd inherited all this data, Kepler worked out that the best explanation of all this was that the planets, instead of moving in circles, or circles round circles, were actually moving in ellipses. So I've drawn a rough diagram at the top right there. You can see that you've got an oval shape, an ellipse, and the sun is not at the center of the ellipse, the sun is to one side. It's a focus of the ellipse. So Kepler worked this out on the basis of observation. If you assume that the planets are moving around the sun in that way, then he found out that the observed motion of the planets fits much better. He published some tables based on these calculations, and they turned out to be over 1,000 times better than any previous method. I think about 1,800 times better, or something like that. The accuracy was phenomenal compared with anything that had been achieved before. So inevitably, over time, it did take time for people to realize how accurate these tables were. The hypothesis got to be accepted. Okay, this makes room for Isaac Newton. Well, Isaac Newton can be seen as following both Descartes and therefore Galileo and Boyle. He looked at these results about the motion of the planets and tried to come up with a theory that would explain them. He was a brilliant mathematician. He was one of the inventors of the calculus, together with Leibniz. And through very clever geometrical calculation and arguments involving calculus, he came to the conclusion that if you postulate a force of gravity acting between objects in inverse proportion to the square of the distance, that means if two bodies are 2 units apart, the gravitational force is a quarter of what it would be if they were 1 unit apart. If they're 3 units apart, the gravitational force between them is 1/9. Now, suppose you have a force like that. So the closer things are, the more gravity there is between them. And suppose you postulate that the force of gravity is proportional to the mass of each body. So the bigger an object, the more gravity there is on it. And suppose you postulate that the acceleration of a body, that is, the amount it deviates from the straight line motion that it would otherwise take, suppose you postulate that it deviates from that in a way that is proportional to the force and inversely proportional to the mass. So the bigger the force, the more it accelerates. The bigger the body for a given force, the less it accelerates. What do you get? And the answer is you get elliptical motion. Now that is a fantastic result. You have this problem that people have been trying to explain for centuries, millennia, the motion of the planets. You have Kepler coming along and giving predictions that are far more accurate than any previous attempt. And hot on his heels, you have an explanation of elliptical motion which is amazingly simple in terms of just one force and one law. Not only that, exactly the same theory with exactly the same equations could be used to explain the motion of cannonballs on Earth. If you drop a stone or throw a stone, the motion can be explained by exactly the same equations that Newton used to explain the motion of the planets. So again, just like Galileo, one of Galileo's big results was that the substance of the moon looked very much like the substance of the Earth, with mountains and valleys and craters and so forth. Now we find that exactly the same laws can be used to explain the motion of both. Newton also proved, incidentally, that a vortex could not generate elliptical motion. It's almost impossible to have a vortex that generates elliptical rather than circular motion. So Descartes' theory, which had never been that popular in Britain anyway, was discredited. Over these years, incidentally, Descartes' theories lingered much, much longer in France than they did on this side of the Channel. There was quite a lot of nationalism about these things. Okay, now let's reflect on this. We've got this wonderful scientific achievement. It's perhaps the most important scientific work ever published, Newton's Principia. But think of that in the context that we were looking at before. We had the background of the Aristotelian theory of motion, which ascribed desires to physical objects, which saw them as analogous to human beings or animals, desiring, striving to reach particular objectives. And that seemed objectionable, occult, weird, spooky. We want to get rid of that. We want to go explain things in a very down-to-earth, mechanistic way, one thing bashing into another. That seems much more comprehensible, much more subject to human understanding and analysis. Okay, Descartes' theory of the orbiting planets fitted in with that, but Newton's doesn't. Newton is postulating this weird force between bodies. How can the Earth be attracted to the Sun unless it knows where the Sun is? How can the Moon be attracted to the Earth unless it knows where the Earth is? It seems very peculiar. So a lot of people objected to Newton's postulation of this gravitational force. They didn't like it because it didn't conform with the ideal of mechanistic understanding. Others, particularly followers of Newton, said, no, it's a proof of God's existence. We know, don't we, that matter cannot think, right? It's the kind of power that matter can't have. Of course, matter by itself can't be attracted to another body either. No, it must be God's action. So it's a proof of God's existence that things move in the way they do. Now, Newton himself took an instrumentalist attitude. Very famous phrase, hypotheses non fingo, I feign no hypotheses. So Newton was asked, what do you make of gravity? Well, he said slightly different things at slightly different times, but the most famous response of his was to say, I'm not going to try to make up any explanation of how gravity works, why it does what it does. All I'm going to say is that the observations are consistent with it working as I described. So I've got these equations which explain how gravity works. Okay, it's proportional to the masses of the two objects, inversely proportional to the square of the distance between them. If you postulate a force like that, it explains the phenomena. I'm not going to go further. I'm not going to try to explain why. Maybe it's God's action. Maybe there's some sort of ethereal fluid that somehow brings it about. But if the behavior of things is explained by this theory, that's good enough. Now, this is I've called it methodological instrumentalism. Instrumentalism is essentially the theory the view that when you have a scientific theory, what matters is the results that it delivers. So let's suppose you have a scientific theory in terms of atoms. As long as it delivers the right results, you don't care about whether there really are any atoms. Maybe there aren't any atoms. Doesn't matter. If the theory delivers the right result, that's good enough. That's instrumentalism. You see a scientific theory as an instrument for delivering results. And Newton took something like that attitude to gravitation, and as we'll see, it was very influential.